Okay, so far we have already known that there are at least two types of plasma. One is thermal equilibrium plasma, and another one is non-equilibrium plasma or cold plasma. Right. And in thermal equilibrium plasma, the important plasma parameters are the Chi degree of ionization, and is the density of charged particle or density of electrons. Okay, and T is the plasma temperature, and Chi, N, and T are related in thermoplasma. And in non-equilibrium cold plasma, we need to know Chi, N, and for the T, so there are three types of the particles in the plasma. So there are electrons, ions, and the neutral gases. So for each particle, they have a characteristic temperature. So we got here electron temperature, ion temperature, and gas temperature. So depends on the system you create. The plasma parameters will change, okay? And besides, we also need to know the electron energy distribution function for your plasma. Electron energy distribution function. So yesterday we have already seen that okay. Electron energy distribution function for a thermoplasma or equilibrium plasma looks like this way. So it follows the Maxwellian velocity distribution function. Right. And the energy of electrons in the plasma equals to 1/2 of mv squared. V is the velocity of electron, m is the mass of electron. So basically, for free electrons, their energy comes from their kinetic energy. Okay. So this is the energy of the electron, and we can also convert the unit of energy to temperature. So the energy of electron equals to 2/3 of kTe. K is Boltzmann constant. Te is the electron temperature. In the unit of Kelvin is absolute temperature in unit of Kelvin. And usually in plasma physics, the energy of electrons is represented by the unit of electron volt, eV. And eV and Kelvin temperature and heat, the molar heat, right? Kilocalorie per mole or kilojoule per mole can be converted. Okay. So if the velocity of electrons in a thermoplasma follows the Maxwellian velocity distribution, and then we can calculate the energy of electrons so that the distribution function of the energy of electron or temperature of electron can be plotted like a curve, like this way. So this is the electron energy distribution function for thermal equilibrium plasma. So in this curve, there are the maximum, the function, the value of the maximum value of this function located at the temperature of Te divided by 2, 1/2 of the electron temperature, 1/2. So if you plot, if you want to mark the 1 times TE, it should be here. It should be here. So this curve, from this curve, we can see the sum of the electrons have energies lower than the electron temperature. And some other electrons have energy higher than electron temperature. So in fact, inside the plasma, the electrons have actually different temperature or different energy, and follows this kind of a distribution curve. This kind of distribution curve, okay? And right here, one mark the dissociation energy. This one mark the ionization energy of the plasma gas. Plasma gas, and later on we will see the importance of this part. This part of electrons has high energy, right? But the ratio of the electron is very small in a plasma. So one call this part as the high energy tail. And later on we will see this figure again. Okay, so in this slide, there are 3 curves. So this curve shows the electron energy distribution function with the electron energy of 1.0 eV. 1.0 eV. So 1.0 is here, right here. But the curve has a maximum value, with energy lower than smaller than 1.0 eV. And this curve is the distribution curve for the electron temperature in a plasma, electron temperature of 2.0 eV. And this curve is the electron temperature of 3.0 eV. 3.0 eV, okay. So based on these curves, we can calculate the ratio of the electron with low energy and with high energy. And this part of the electron is named the high energy tail. Okay, so let's come back to this figure. Okay, so for example, the argon gas has ionization energy around 15.7 electron volt. Right, from the previous picture here. In order to ionize argon, one need to apply an energy higher than 15.7 eV. So this energy is also known as the ionization energy of argon atom. Okay. Okay. So if you have an argon plasma, this energy is related to the equation of electron impact ionization. Okay, so if the gas is argon, and then this energy is around 15.7 eV. 15.7 eV. Okay, so from the particle collisional process, one needs a primary electron with energy higher than 15.7 eV to ionize argon atom. Right? After argon atom is ionized, the argon atom will release one electron. And this process is named electron impact ionization. Right? And the electron here is the primary electron. And one of these electrons here is secondary electron. And the other one is the electron after collision. It comes from the primary electron, but with less energy. And this equation or this reaction is the most important reaction in plasma physics, because this process can increase the number or the density of electrons, increase the density of electrons, or this reaction can create ion and electron pairs. Ion and electron pairs. And the ion and electron pairs are the most important constituents in plasma. Okay. So from this figure, we can find out even though in this plasma, the electron temperature is around maybe around 7 eV or less, or 1 eV or 2 eV, but in this region, the high energy tail, there are small amount of electrons, having energy higher than 15.7 eV. So in a plasma, in an argon plasma, right, a typical plasma condition, for example here, the average electron energy is about 2 electron volts, but you can still create plasma. Because for a 2 electron volt electron temperature, actually there are small amount of electrons, with energy higher than ionization energy of the respective case. Okay, so this part is very important. From the energy distribution function, and one can see in this figure. This is an electron with the average energy of 1 electron volt, and 2 electron volt, and 3 electron volts. Okay, and this part is high energy tail. Okay, so even though the average energy of electron is 2 electron volt or 3 electron volt, there's a small amount of electron with energy higher than the ionization energy of specific case. Okay, and this curve follows the Maxwellian velocity distribution, and it's good for the thermal equilibrium plasma. And if we generate plasma by using electrical field, right? The electrical field will influence the distribution function of electrons, electron energy. Okay, because in an electrical field, the electron can be accelerated so that the energy will increase. So the average energy of electrons will increase by the electrical field. Okay. Yeah, from if the electrons travel for a certain distance within an electrical field, the electrons can gain energy, such amount of energy. Okay. So if you generate plasma by using the electrical discharge method, the electron energy distribution curve will change. So in this figure, there are dashed line here. Dashed line here is the thermal equilibrium plasma. For thermal equilibrium plasma, the electron energy distribution curve, the function follows the Maxwellian distribution. And if you apply an electrical field to a plasma, the electrical field will increase energy of electron so that the curve shift toward high energy side, right? So the solid line here shows the electron energy distribution curve for a plasma with applied electrical field. So the average energy of electrons increase so that the curve shift to a lower, higher energy region, because the electrons gains energy from electrical field by this equation. But in this figure, one can find out the curve doesn't follow the Maxwellian distribution. It doesn't follow Maxwellian distribution. So, in fact, here is a drop. Is a switch point. So at the high energy tail part, right, the electron energy distribution curve doesn't follow the Maxwellian distribution, but it will drop at this point. And this point is related to the threshold energy or the ionization energy of the gas. Okay, because there are more high energy tail, right, after you apply an electrical field to your plasma system. So there are more high energy electrons. But these electrons collide with gas atom and cause ionization. So the electrons lost their energy after the collision process. After collisional process, so that this curve will drop at the threshold energy or ionization energy. Okay. And in this figure, I got this picture from Chapman's book, The Growth Discharge Processes, that book. Okay. So he also include the collisional process curve to this figure. The collisional process curve is this curve. So he also include a curve. Okay, for the ionization process to the same figure, right? Okay. So this is inelastic collision cross-section. And so today I will go through this inelastic collisional process and the collisional process. Okay, yes. Inside plasma, the electrons only travel for a certain distance, right? And then they can collide with other particles. Okay, so So there are multiple collisional processes. The multiple collisional process will induce a distribution curve, follow the Maxwellian distribution if there is no electrical field, right? So if we apply electrical field, in average, the energy of electron increase. But for those electrons with energy higher than ionization energy of argon gas, when they collide with the argon atom, they lost energy, right? And if the energy of the electron is less than the ionization of the argon gas, when the electron collide with the argon atom, they might just undergo elastic collision. So they change their direction, but the energy remains the same. So that's the reason. That's the reason if the energy is smaller than the threshold energy or ionization energy of the gas, right? The average energy of the electron increase. That's the reason that the curve shift to a higher energy region. But if the energy of the electron is higher than the ionization of the gas, argon gas, right? Those electrons cannot remain as high energy state after collision, after collisional process. That's the reason the curve start dropping here. They contribute to the electron impact ionization process. Okay. Okay, so next few slides describe the collisional process in plasma, including elastic collisional process and inelastic collisional process. But before we go through the collisional process, we have to know the concept of the mean free path, and the collision cross-section. Okay. So in this figure, it shows in a system, right? In a system here or in a volume we studied, there are gas atoms. So the gas atom keep traveling, right, with certain speed, and then after the gas atom travel a certain distance, they might meet another gas atom. So there's a collision. And if this is elastic collision, the gas atom might change their direction, but the energy remains the same. Elastic collision. Okay. So in a gas phase, all the gas molecules undergo a multiple collisional process. So if we take a statistic analysis, we can get an average distance for an atom travel, right? For a gas atom travel before it collides with another gas atom. And this distance is named mean free path. Okay. So later on in the next two slides, we can see that the mean free path is inversely proportional to gas density. Okay. And inversely proportional to the effective area or effective cross-section of gas molecule. Okay. And in this slide, if we take argon gas, for example, argon gas at room temperature. So based on the ideal gas law, you can get other properties of argon gas. argon gas, right? You can calculate the density of the gas in 1 atmospheric pressure, right? And you can also get the density of the argon gas at lower pressure, okay? So in this table, the pressure is listed here. 1 torr, 10 to minus 1, 10 to minus 2, 10 to minus 3 torr. So 1 atmospheric pressure equals to 760 torr. This is a pressure unit, right? Equals to 760 torr, or close to 1,000 torr, close to 1,000 torr. So for a gas with a pressure of 1 torr, its pressure is less than 1 atmospheric pressure. So sometimes we call this as the reduced pressure. Or sometimes we call this kind of the pressure as vacuum. Vacuum, okay. So if the gas pressure is 1 torr, the mean free path for the argon gas is 0.005 centimeter. So it's very small, very small. So the gas only travel for a short distance, and then the gas will meet another gas atom or another gas molecule, and then collide with each other, and then change the direction of the traveling. Okay, and if the gas pressure is 10 to minus 3 torr, and 10 to minus 3 torr, right, is millitorr. Ten to minus 3 torr is 1 millitorr. So sometimes we can just write down 1 m torr, 1 millitorr. Okay. So if you run a sputtering system, so in the application part of this course, there's a chapter of sputter deposition. So in the sputter deposition system, we can use the plasma with the pressure around 1 millitorr. 1 millitorr, can be used for sputtering process. Okay, and if you want to run a plasma enhanced chemical vapor deposition process, you need a higher pressure to generate stable plasma. So the pressure usually is between 10 to minus 1 torr, right, to close to 1 torr, or usually it's less than 1 torr. So around 10 to minus 1 torr. Okay. So with such kind of the pressure, we can estimate the mean free path of the argon gas. So so if the pressure is 1 millitorr, the mean free path of argon is around 5 centimeter. 5 centimeter. Okay. So the mean free path here can be used to design your system. Okay. So usually when we set up the system, we need a chamber. So the size of the chamber needs to be larger than the mean free path. Of the gas atom, larger. Okay. And later on in next week, in the next chapter, you will also learn the Debye length. Debye length is also very important in a plasma, okay? So when you design your plasma system, the size of your chamber also need to be larger than the Debye length, Otherwise, there is no plasma. You cannot, there is no plasma exists in a space, no, small, too small, okay? So if you make a system with, and run a system at the pressure of 10 to minus 3 torr, the system must be larger than 5 centimeters. Must be larger than 5 centimeters. But if you want to make plasma enhance the chemical vapor deposition, the operating pressure is higher, right? The mean free path become very small. So when you build up a system, maybe the dimension of your system can be less than 1 centimeter. The distance between electrodes can be less than 1 centimeter. Okay, but usually you will not make such small system. Maybe you can make it with a dimension of 2 centimeters if you run the process at higher pressure. Okay. Okay, this slide shows the correlation of the mean free path and the collisional process. Okay, and I think the handout I gave you, I upload to a Moodle system is this slide. So all this information came from the Chapman's book. You can read the detail, okay? And here is a mistake. So there n times q equal to 1 over lambda. Right here, not equal to lambda. 1 over lambda, okay? Okay, so in this slide, the story is about the relation of the collision cross-section, and the mean free path, and the density of gas, and the cross-section, effective cross-section of a gas molecule. So this slide is a brief description of the collisional process, collisional cross-section, and the mean free path. So assume there is a slab of volume with the area, okay, the cross-section area of A, and the thickness of delta X, okay? And there are gas molecules or gas atoms inside this volume. And to make it simpler, we can assume all the gases are stationary or they cannot move. They are fixed at these locations. So if an electron travels from the left side toward the right side, or if another gas molecule travels from left side toward the right side, right? When this electron passes through this thin slab, we can calculate the probability of collisional process. Okay? So in Chapman's books, he used one section, around 2 pages, to describe the analysis of this process. Okay? And the result is this equation. if the cross-section of the quartz molecule equal to sigma, or in another in the next slide, it also equals to Q. Okay, if it's sigma or Q, represent the cross-section of a molecule. And if the mean free path of molecule equals to lambda, mean free path. Okay, so that we can see it in another way. So this molecule can occupy the space like a cylinder, with the volume of sigma times lambda. So in this slab, we can calculate the the volumes occupied by molecules by multiply the sigma and lambda with density of electron. Okay. So if this value is large, then the collision probability is larger. So if this value n times sigma times lambda is small, and then the collision cross-section or collision probability is small. Okay, so the analysis used to correlated collision cross-section with the probability of collisions. Okay, so the cross-section and the probability can be compared. So that's the reason. In this process. Sure. In this figure, right, the electron impact ionization of inner gas, the vertical axis has a unit of ionization cross-section. And the unit is here, pi times A0 squared. A0 is the bore diameter. Okay, so actually the cross-section, the unit of cross-section represent the probability of the interaction. Okay? Okay, so in the next slide, okay, we can go through the different collisional process. Okay, and in this figure, this figure also came from Chapman's textbook. So he included different type of collisional process in one figure. So if you have a system filled with argon gas, and generate a plasma, there are different collisional process. Happens in your system. So the upper curve shows the momentum transfer. So this part belongs to elastic collision. Okay, and this figure shows the ionization of argon atom into a monovalent argon ion. And this curve shows the ionization of argon atom into a divalent argon ion. Divalent argon ion. Okay, and the horizontal axis is the energy of electron. So this part is electron impact ionization, right? And the upper curve is the electron impact momentum transfer process. So there are different kind of collisional process. So include elastic collision process, excitation, ionization, attachment, and other processes. So next few slides will explain this collisional process. And the sigma T is the total collision cross-section. So including all this collisional process. But we can also just look at individual collisional process. And the unit here, right? The probability is represented by the cross-section with the unit of centimeter square. Centimeter square, okay. That's the reason came from the correlation of mean free path, the density of gas, and the cross-section coming from this analysis. So we use the collisional cross-section concept to describe the probability of elastic and inelastic collisions. And this is the first collisional process. So it's elastic collision. So right here is a gas atom. So in a gas atom, you can draw at the center. The center is the nucleus, right? And then electrons will travel around, in this region. Okay. So here are the electrons, and here is the nucleus of an atom. So if a free electron in a plasma travel for a certain distance and then collide with this atom, okay, it might reflect and change the direction. But during this collision, if this collision is elastic collision, we can still calculate the ratio of energy transferred during this cross-section. So this is from the basic physics, right? In Newton's analysis. So the energy transfer, the ratio of energy transfer during the elastic collision is equals to 4 times the mass of the electron. This is the impact electron, and T is this atom. So usually we can use the target atom. T means the target atom. Okay. So the energy transferred during the elastic collision equals to 4 times MT divided by Mi plus MT and square. Okay. So here are the mass of impact electron and mass of the atom. Since the mass of the atom is much larger, right, than the mass of electron. So you can estimate the ratio of energy transfer. So it's very small. Okay. So after the collisional process, the total energy remains the same. Then the atom remain as neutral state, right? And the electron change its travel direction, and the atom also change, but the atom only change a little bit because of the mass ratio. The mass ratio. Okay, we can assume that the atom was not affected by the collision, and the electron just reflect by the atom. Okay, so such kind of process is called elastic collision, and this process does not contribute to plasma generation. Does not contribute, okay, to plasma generation. And here is the cross section of elastic collision, and sometimes you can also call this as a scattering process. Scattering. So from the vertical axis, we can see the cross section is around, for example, here, the maximum is around 14 or a little bit 20 times 10 to minus 16 centimeters square. Okay. So this is the probability of successful collision, or also known as described by the cross section. Okay. So this is the first part. Elastic collision. And the second process is the electron impact ionization, and we have already seen this equation and this process several times. Okay, so from the figure shows here, an energetic primary electron collide with a neutral gas atom, right, and cause the release of one electron from the neutral gas atom, and this electron is named secondary electron. And the original primary electron lost energy, and then it will still travel inside the plasma, and this electron becomes residual electron. Okay. So in this equation, here is the primary electron, and on the right side of the equation, there are two electrons. One is the secondary electron, the other one is the residual electron. And neutral atom become ionized, right, to create electron and ion pair. And if we just count on the number of electrons, we can find out the number of electrons increase by this process. So this process is most important process in plasma in sustaining the gross discharge. Okay, so in the next chapter we will see the loss of charge. So once you generate the plasma, the electrons will lose to somewhere. In order to sustain the plasma, you need to supply new electrons in your system. And this process is the most important process because you can supply new electrons. Okay?